Have you ever wondered what it would feel like to walk all the way to the edge of the universe and look out over whatever waits beyond it? If this kind of quiet cosmic wondering brings you a sense of calm, a soft like or a gentle tap on subscribe truly helps keep this little calm corner of the universe glowing for you and for others who drift through the night searching for peace in the stars. As you lie here now, your body resting, your room still, your breathing moving in its own slow rhythm, your mind can begin to drift outward, far beyond the ceiling, beyond the roof, beyond your city and the dark curve of the earth, into a larger picture of where you are and what it could even mean to talk about an edge of the universe. You feel still, almost motionless, yet right now the earth is spinning beneath you, carrying you around its axis at hundreds of meters each second, depending on your latitude. And that spinning globe is orbiting the sun at about 30 kilometers every second, and the sun itself is circling the center of the Milky Way, and the Milky Way drifts with countless other galaxies through expanding space. Your body is quiet. Your day has loosened its grip, but you are already part of a vast motion, a gentle migration through something so large that the word edge starts to become difficult to pin down. When people ask what lies beyond the edge of the universe, they often imagine the universe as if it were a kind of giant bubble, floating in a darkness that is not part of it, with a surface that you could touch, a boundary you could step across. Inside the bubble, stars and galaxies and light outside, some unknown emptiness, some other region, perhaps another bubble that belongs to a different universe entirely. You might picture yourself drifting in a spacesuit, approaching that glowing edge, reaching out a hand to touch the wall of reality, and then peering through it into something else. To understand why this picture is both beautifully intuitive and yet deeply misleading, let your attention sink gently into a simpler idea. The idea of where you can see right now. Even with your eyes closed, you know that your vision has a limited range. You cannot see beyond walls, beyond the horizon, beyond a certain distance. In the same way, the universe you can observe has a boundary, not because there is a physical wall there, but because light has only had a certain amount of time to travel since the beginning of cosmic expansion. The universe is about 13.8 billion years old. In that time, light has been racing outward at 300,000 kilometers per second, and as space itself has stretched, that light has been carried along with it, reaching you from farther and farther away. If you could float in a perfectly dark void and switch on an incredibly sensitive instrument around you, you would be able to detect a spherical region of information, a bubble of visibility centered on you. In every direction, you could see galaxies out to a distance of about 46 billion light years. Not because they are older than the universe, but because as light travels, the fabric of space itself stretches, carrying those galaxies away while their photons still struggle toward you. Beyond that distance, there are galaxies whose light has not yet had enough time to reach you since the beginning of expansion. They are real. They exist. They are part of the same continuous structure. But for you, for now, they are beyond the horizon. This is the observable universe. It has a kind of edge, but that edge is not a wall. It is a limit of what you can currently know, a boundary drawn by time and light rather than by some cosmic material. You might imagine sitting in a quiet field at night, surrounded by fog. Close to you, the silhouettes of trees are sharp and visible. Farther away, shapes soften, blur, and then vanish into the thick gray. You would not say that the world ends at the distance where the fog hides it. You only recognize that you cannot see beyond that point. In the same way, your cosmic fog is the finite speed of light and the finite age of the universe. So already there is a first gentle shift. When you ask what lies beyond the edge of the universe, the first answer is that there is no evidence of a hard edge at all, only a horizon of visibility. Beyond the horizon, as far as our best theories suggest, the same kind of cosmic fabric continues. More space, more galaxies, more structures shaped by gravity and time, though forever hidden from you. Your not seeing them does not make them unreal. They are part of a larger whole that you are woven into. Let that thought settle as you breathe in and out. You are not at the center of everything in some special sense, yet, from your point of view, the observable universe is a perfect sphere with you at the middle. If another observer were sitting in a galaxy billions of light years away, their observable universe would also be a sphere, centered on them, overlapping with yours, but extending into regions you will never access. There is something quieting in that every conscious being anywhere would feel at the center of their own sphere of visibility. And in a way, they are. Now, consider the universe itself, not as an object floating in some external container, but as everything that physically exists according to our best models. The equations of general relativity that describe how space-time curves and expands do not need a larger surrounding space. They describe the geometry of the universe from the inside. The universe does not expand into something else in those equations. Distances between galaxies grow, like dots on the surface of a stretching balloon, but the balloon metaphor can mislead you. You imagine the air around the balloon, and you think of that as some kind of outside. In the true mathematics, there is no air, no external room. There is only the surface itself, only the relationships between the dots. Imagine instead that you live as a tiny creature confined to the two-dimensional surface of a vast sphere. You can walk north, south, east, west. If you travel in a straight line, you eventually loop around and return to your starting point. You never leave the surface you cannot step off into a higher dimension. For you, the surface is all there is. If someone asked you where the edge of your world is, you might search for a cliff, a boundary where the surface stops, but you would never find one. Your universe would be finite in area, yet without an edge. You could keep walking forever. Our universe might be like that. It might be finite in volume yet without a boundary, curved back on itself in a higher dimensional way that you cannot directly sense. Or it might be infinite, stretching without limit in all directions, with no curvature large enough to wrap back around measurements of the cosmic microwave background. The pale afterglow of the Big Bang that bathes all of space in a faint cold light suggest that on the largest scales our universe is very close to flat. If it is perfectly flat, and if that flatness persists everywhere, then space may be truly infinite. In an infinite universe, the question of what lies beyond the edge dissolves, because there is no edge at all, only an endless continuation of the same statistical pattern of galaxies and voids. Pause for a moment with that idea lying where you are now, eyes perhaps growing heavier. You are part of something that, in one possibility, has no boundary whatsoever. No outer rim, no last galaxy, no final outpost of matter. Everywhere is center. Everywhere is inside. Everything that exists is part of an unbounded fabric that has no outside at all. In such a picture, Asking what lies beyond the edge of the universe is a bit like asking what is north of the North Pole. The question melts as you try to hold it, leaving behind a quiet recognition that sometimes edges are illusions created by the way we imagine space rather than properties space itself has. Still, your curiosity does not have to stop there, because there are other senses in which something like an edge may exist, not as a wall in space, but as a boundary in time. The standard cosmological model tells you that in the distant past, the universe was hotter, denser, more uniform. If you let the clock run backward, galaxies merge, atoms break apart, particles crowd closer until they form an almost featureless sea. This picture, extrapolated far enough back, reaches a point beyond which the equations break down, a singularity in the mathematics. We call this the Big Bang, but that name can be misleading too. It conjures an image of an explosion in pre-existing space, with fragments flying outward into an empty background. In reality, the Big Bang is not an explosion in space. It is the rapid expansion of space itself from an earlier, extremely compact state. Space and time themselves are emerging, cooling, unfolding. So, if you trace everything you can see, now, back through time, you approach a boundary in your description. Not a place you could visit, not a wall you can touch, a limit to how far you can meaningfully talk about earlier moments. Beyond that temporal edge, your equations grow silent. What lies beyond it may be another phase of reality, some quantum gravitational state that does not resemble space and time as you know them. Or it may be that your language of before and after simply fails there, the way left and right fail at a single point. Let your mind rest lightly in that ambiguity. Not every question has a crisp answer framed in the concepts you are used to. Some questions mark the outlines of where your current understanding begins to thin, where familiar ideas can no longer be trusted. Beyond the earliest moments you can describe with physics, there may be no before in the ordinary sense, just as there is no time before time. When you feel your thoughts stretching to accommodate that, notice how the muscles of your attention relax when you stop forcing a clean picture and allow the unknown to remain unknown. Then, there is another idea that often comes when people ask about the edge: the multiverse. If the universe began in a period of extremely rapid expansion called inflation, a moment when space doubled and doubled again on unimaginably short timescales, then our observable universe might be just one pocket, one region where inflation ended and hot matter and radiation formed elsewhere. Inflation might still be going on, spawning other regions, other bubbles with their own local Big Bangs. In some versions of this model, space on the largest scale is like a foam, with countless expanding pockets. Each pocket has its own observable universe, its own horizon, its own galaxies, and maybe its own laws of physics. In that picture, you could say that beyond the edge of our observable universe, beyond the regions whose light will ever reach us, there may be vast portions of space-time that we will never see. And beyond those, perhaps other bubble universes separated by inflating space. Yet even here, the idea of an edge is subtle. You cannot travel from one bubble to another. There is no simple wall where one universe stops and another begins in a way you could put your hand on. Instead, there is a patchwork of regions with different properties, all part of a larger structure described by a deeper theory. Think of waves on a dark, calm sea at night. From where you rest on a small boat, you see only the ripples near you, the glints of starlight on peaks and troughs. You know, in your mind, that the water extends beyond the circle you can see. You may even know that far away the sea is doing something different. Storms, currents, quiet bays. Yet you never leave the surface. You never rise above to see the entire ocean at once. For you, the horizon around your boat is the edge of what you can know. Beyond it, the sea continues, but only in imagination and in the equations that describe how water behaves. So it is with these cosmic speculations. They are not fantasies spun out of nothing. They are grounded in theories that have been tested in other ways. Inflation, for example, helps explain why the universe looks so uniform in temperature across vast distances and why it is so nearly flat. But the idea of other bubble universes is, for now, beyond direct test. It lives at the frontier of what you can responsibly talk about with physics and what you must hold more loosely as a maybe, a possibility that fits the mathematics but has not yet stepped into the light of measurement. As you sink more deeply into this gentle maze of ideas, notice how often your mind tries to draw a picture, to imagine the universe from the outside, as if you were a spectator looking down on a glowing sphere. Then remember that every real observer is inside. There is no balcony, no place to stand outside space-time. Even your thoughts are patterns of matter and energy unfolding within it. The question what lies beyond the edge of the universe is, in a sense, a question about a perspective you cannot actually occupy. You are woven into the thing you are asking about. Let that realization soften the edges of the question itself. Instead of trying to see the universe from without, feel your way into what it means to exist within a reality that may be unbounded. You are not near the edge or far from it. You are not central or peripheral. You are a local pattern in a vast, perhaps endless field, a fluctuation of atoms and awareness, arising in one small region of a cosmic fabric that may have no boundary and no outside. Your breathing is slow. The room around you is quiet. The distance between your body and the nearest star is so large that light takes years to cross it. Yet in your mind, you can span that gap in an instant. You can picture your planet shrinking beneath you, your city becoming a faint, glowing web, your continent fading under clouds, the earth itself turning into a marble of blue and white. You can drift farther and see the orbit of the moon as a pale, silvery ring, then the trails of the planets curling around the sun. You can watch the sun slide into its orbit around the galaxy, the Milky Way appear as a spiral of light, a pinwheel drifting with others in a cluster, and that cluster itself just one node in the cosmic web of filaments and great voids. At some point, when you pull back far enough in your imagination, you reach the limits of what you have ever seen in photographs, in simulations, in diagrams. Beyond that, you are guessing. You are extending patterns you know into a domain you have never touched. That is, in a quiet way, what cosmologists do with their models. They take the parts of the universe they can see, they measure the cosmic microwave background, the distribution of galaxies, the subtle ripples in structure that betray the influence of dark matter and dark energy, and they infer what the larger whole might be like. They cannot point a telescope at the true edge of everything, because if there is such an edge, it lies outside any field of view they can ever reach. Instead, they read the universe as you might read a coastline from the shape of the waves, learning about unseen depths by watching what touches the shore. In that sense, your question becomes a kind of meditation on limits. What can be known from within? what must remain outside your grasp, and how to be at peace with that. The universe may have no edge in space, and yet it will always have edges in your knowledge, horizons that recede as you learn more but never disappear. Every time you extend your reach, you uncover new mysteries. Every answer opens a deeper question. As you rest here, you embody that process. Memories from your day float in, then drift away. You think for a moment about the farthest galaxy ever observed, a smudge of light whose photons began their journey more than 13 billion years ago, long before your planet formed, long before the atoms in your body were forged in stars. Then you think about distances beyond that galaxy, regions you will never see, not because they do not exist, but because in this universe, information can only travel so fast and time has only passed for so long. Your life unfolds inside those boundaries. Your thoughts about beyond are real as thoughts, but the places they point to may forever elude direct contact. In that realization, there is a quiet kind of humility. You do not command the universe. You do not stand outside it, surveying it like a completed map. You are more like a small lantern of awareness, moving through one tiny patch, lighting up a few nearby shapes for a brief span of time. Outside the reach of your light, the landscape continues into darkness. Not a hostile darkness, just a calm, indifferent expanse that does not need to be seen to be there. Let that image soften and fade. Let the word edge lose some of its sharpness. Instead of a hard boundary, imagine gradations of visibility, of certainty, of understanding. Close to you, things feel solid and clear. Farther away, they become more abstract. Equations on paper, signals in detectors, spectral lines, and redshifts. Farther still, they become possibilities. Hypotheses about inflation and multiverses and quantum gravity, sketched in chalk, revised, refined, sometimes erased. Beyond even those, there is a space of pure unknowing, a region where questions like what lies beyond the edge of the universe transform into something more like poetry, more like the quiet awe you feel when you stand alone at night and look up, knowing that the sky you see is only the faintest hint of what exists, and that your mind, while powerful, is still a small and finite thing looking into something that may have no boundary at all. In that space of not knowing, your breathing becomes the most reliable rhythm. In, out. The gentle gravity of your bed holds you. The subtle pull of the earth holds the bed. The sun holds the earth. The galaxy holds the sun, and the universe, whether bounded or boundless, holds the galaxy in a web of relationships described by laws you only partly understand. You do not need to resolve the question tonight. You can let it remain open, like a window that never quite closes, always letting in a little cool air from the unknown. What lies beyond the edge of the universe may be more universe. It may be a larger structure in which our entire cosmos is only a small region. Or it may be that the concept of beyond stops making sense at some level. The way outside does not apply to the surface of a sphere when you are confined to the surface itself. For now, it is enough to know that your curiosity reaches out to that boundary, even if your instruments cannot, and that this reaching is part of what it means to be human in a vast, ancient, and possibly edgeless reality. And as you lie here, held gently by the quiet of your room, the question of what lies beyond the universe begins to sharpen into something more than poetry. Because although no observer can step outside cosmic expansion, the theories built by people like Alan Guth, Andre Linde, Stephen Hawking, Abhay Ashtekar, and the researchers who mapped the early universe with the WMAP and Planck satellites do not leave you drifting with only metaphors. They offer shapes, possibilities, models that reach just far enough beyond the horizon to give your imagination something steady to rest on, even as the darkness stretches endlessly outward. One of the strongest clues comes from the cosmic microwave background itself. The faint afterglow released about 380,000 years after the Big Bang. The Planck mission, launched by the European Space Agency, mapped that glow with exquisite precision. Tiny variations in temperature, only millionths of a degree, appear as speckles across the sky. Those speckles are not random. They trace the density waves of the early universe. And the statistics of those waves, their size, their alignment, their distribution, tell you something profound. On the largest observable scales, space is extremely close to flat. If space is truly flat or nearly flat, the simplest interpretation is that it extends far beyond the region you can see, possibly infinitely far. A universe without boundary in space, continuing endlessly in all directions. This is one real possibility, that beyond the observable horizon lies simply more universe, more galaxies, more clusters, more dark matter halos forming and dissolving over billions of years. Nothing special, nothing exotic, just more of the same cosmic fabric stretching outward without limit. Inflationary theory supports this view. Alan Guth's original idea that, in its earliest moments, the universe expanded exponentially fast, inflating from subatomic scales to macroscopic ones in a fraction of a second, naturally creates a space that is much larger than anything we can observe. André Linde's later work on chaotic inflation argues that this expansion likely didn't end everywhere at once. Some regions would slow and settle into a universe like ours. Others would continue inflating, creating an ever-growing mosaic of regions, some cooling into universes, others racing outward in a runaway expansion. From your resting place now, this paints a picture that almost feels like breathing. Pockets of space-time exhale into calm, cooling universes. The space between them inhales into endless inflation. In Linde's mathematics, what lies beyond the edge of the universe is not emptiness, but a larger inflating field that forever pushes distant regions beyond each other's horizons, severing causal contact between them. They exist, but you can never reach them. You can never see their light. They might host galaxies, or entirely different physics, or simply remain cold and empty. They are real solutions to the equations, not fantasy. Yet another grounded possibility comes from loop quantum cosmology, the branch of quantum gravity led by researchers like Abhay Ashtekar, Parampreet Singh, and others. In this framework, space-time is not infinitely divisible. It has a granular structure at the Planck scale. These models suggest that the Big Bang may not have been a beginning at all, but a bounce. When the universe contracts toward extremely high density, quantum geometry creates a repulsive force that prevents true singularity. The collapse rebounds into expansion. If this is true, then beyond the edge of our universe in time lies an earlier universe that shrank, bounced, and gave birth to this one. Not metaphor. An actual prior cosmological phase predicted by the equations. As your mind drifts through that picture, the idea of beyond shifts again. Not beyond in space, but beyond in time. You might imagine the universe like a heart, beating slowly on unimaginable timescales. Expansion, contraction, bounce, expansion again. Each cycle wiping clean the structures before it, yet carrying forward subtle imprints in the cosmic microwave background. faint clues that researchers like Anna Igis and Paul Steinhardt have sought in observational data. No evidence so far confirms a bounce, but nothing rules it out either. And if our universe truly emerged from a previous one, then beyond the edge of our universe is simply another era, another cosmic chapter that ended long before matter cooled into stars and planets and people. There is also the ekpyrotic universe model proposed by Steinhardt and Neil Turok, which envisions our universe as one of two higher-dimensional brains that occasionally collide. In that framework, the Big Bang was not an explosion, but an impact, a meeting of vast, multidimensional surfaces moving in a higher-dimensional bulk. What lies beyond our universe, then, is not nothingness but another brain, parallel to ours, drifting through the higher dimensional space predicted by string theory. No poetic metaphor, an actual physical structure whose existence could, in principle, leave faint gravitational signatures in the cosmic microwave background or in the distribution of primordial gravitational waves. And yet another possibility, one suggested by eternal inflation, is that beyond the observable universe lies a region still inflating so rapidly that no signal can ever cross into ours. Inflation would stretch that region faster than light can travel, not violating relativity, because relativity limits motion through space, not the expansion of space itself. If this version is true, then beyond our horizon is a place frozen in an almost featureless state, with no galaxies, no atoms, no structures, only a quantum field locked in an extremely high-energy configuration. That region would never cool into stars or planets. It would never give rise to life. It would simply remain in eternal expansion forever. A real physical possibility, one strongly supported by the mathematics of inflationary potentials. Slowly, these ideas begin to form a pattern. They are not random fantasies thrown into the dark. They are built from Einstein's equations, from satellite maps of the cosmic microwave background, from the particle physics experiments at CERN, from redshift surveys measured by telescopes like Hubble and JWST, from the statistical fingerprints inflation leaves in polarization patterns of ancient light. They come from attempts to answer questions honestly with the tools you have, even when those tools must reach into energies and scales you cannot yet observe directly. And as you lie here, the idea of beyond becomes softer and more tangible at the same time. You begin to feel how the universe, as vast as it is not infinite in mystery. That real knowledge exists about regions you cannot see. That scientists have built real mathematical structures that extend the world beyond your horizon in rigorous, testable ways. And while none of these possibilities have been confirmed, each one offers a shape to the unknown, a direction for your curiosity to rest upon. If the universe is spatially infinite, then beyond the edge lies simply more universe. If inflation is eternal, then beyond the edge lies still inflating spacetime. If the ekpyrotic model is correct, then beyond the edge lies another brain. If loop quantum cosmology is correct, then beyond the temporal edge lies a previous universe. If cosmic inflation ended unevenly, then beyond the edge lies other bubbles with different physical constants. If the universe is finite but unbounded, then there is no beyond at all, only a geometry that curves back on itself. And you feel how each possibility carries its own kind of quiet beauty. Not answers that close a door, but answers that open deeper spaces within the night, allowing your thoughts to drift not into confusion but into a calm wonder, grounded in real scientific work. Your breathing slows, the shapes around you soften, and the universe expands outward in your mind, not into emptiness, but into a tapestry of possibilities woven from experiments, equations, and the patient work of people who spent their lives looking into darkness and pulling faint patterns of truth from the silence. This widening sense of what the universe might be leads naturally to the question of whether the space you observe is only a small region of a far larger cosmic structure. Evidence gathered from the cosmic microwave background shows that the fluctuations imprinted on that ancient radiation follow patterns predicted by inflationary theory with remarkable accuracy. The nearly scale-invariant distribution of temperature variations, the slight preference for certain angular correlations, and the overall uniformity across the sky all point toward a moment in the young universe when space expanded faster than any signal could traverse it. That brief but immense expansion smoothed the cosmos and stretched quantum fluctuations into the seeds of galaxies. And while the part you can see appears finite, the mathematics describing inflation strongly suggests that the process did not end everywhere at once. In many inflationary models, once the expansion begins, large regions of space continue inflating indefinitely, while smaller pockets break away into calmer expansion and form universes like ours. Researchers such as André Linde and Alex Vilenkin have explored this behavior in depth, showing how quantum fluctuations within the inflationary field create pockets of stability within a broader sea of ever-expanding space. These pockets cool, condense, and mature into structures resembling the cosmos you observe. Around them, the space that never left inflation stretches faster than any particle or photon could ever cross. This means that beyond the limits of everything visible lies not an absence but a dynamic, high-energy domain that remains forever inaccessible, its expansion rate locking it beyond reach. The implications are vast. If inflation truly behaves this way, then the universe is not a single object with a single boundary, but a branching structure, with regions of space continually budding into existence. Each newly cooled region becomes its own universe with its own history, governed by the same underlying laws, but potentially shaped by different initial quantum conditions. This model transforms the idea of an edge from a physical barrier into a horizon defined by the limits of causal contact. Anything beyond that horizon may exist in abundance, yet no information from those regions can ever reach you. What lies beyond the universe, in this view, is simply the continuation of a broader landscape where universes form endlessly, like droplets crystallizing out of a supercooled mist. As you follow this idea deeper, another possibility emerges from the study of topology. The equations of general relativity allow for shapes that extend far beyond simple spheres or infinite planes. Space might be finite yet unbounded, looping back on itself in ways that require higher dimensional thinking to visualize. Researchers such as Jean-Pierre Luminet and mathematicians exploring cosmic topology have studied whether the universe could possess a shape similar to a three-dimensional analog of a torus, or even more complex manifolds. In such a cosmos, traveling far enough in one direction might, in principle, return you to a region that appears new, but is actually a continuation of the same space. Although no repeating patterns have been conclusively identified in the cosmic microwave background, the possibility remains because the characteristic scale of such topological features could lie beyond the observable limit. If true, then beyond the visible universe lies not external territory, but a deeper continuation of the same manifold, folded in a way that prevents any simple notion of outside. The universe would be finite yet without edges, contained entirely within its own geometry. From here, the landscape broadens further into the domain of quantum gravity. Loop quantum cosmology, developed by Abhay Ashtekar, Parampreet Singh, and others, replaces the classical notion of continuous spacetime with a discrete structure at extremely small scales. In this framework, the Big Bang is not a singular beginning, but a transition from a previous contracting phase into the current expansion. The mathematics shows that as the universe contracts, quantum effects generate a repulsive force that prevents density from reaching infinity. Instead of a beginning, there is a bounce. If this model reflects reality, then what lies beyond the early universe is another cosmological epoch, perhaps similar in structure, perhaps profoundly different, connected not through an edge in space but through continuity in time. Some researchers have even proposed that subtle features in the cosmic microwave background could originate from events that occurred before the bounce. These features include slight power anomalies on large angular scales and statistical asymmetries that deviate from perfect isotropy. While none have been definitively tied to a pre-bounce universe, they remain areas of active investigation. If any such features prove meaningful, they could provide the first observational window into a time before the conventional Big Bang, extending the frontier of what lies beyond into a domain that predates the known universe itself. Other theoretical frameworks propose even more dramatic visions. The ekpyrotic and cyclic models advanced by Paul Steinhardt and Neil Turok suggest that the universe originates from collisions between vast higher-dimensional surfaces known as branes. In these models, the Big Bang corresponds to the moment of impact between branes, releasing energy that fills space with matter and radiation. The universe expands, cools, and then eventually recollapses in preparation for another collision. If this view is correct, then beyond the universe lies a higher dimensional space containing other branes, each potentially carrying its own version of reality. The edge becomes not a place but a transition, an interface between multidimensional structures whose interactions give rise to entire epochs of cosmic history. These models differ profoundly, yet they share a common thread. They each propose that the observable universe is only a fraction of a much larger reality. Whether through endless inflation, complex topology, quantum bounces, or higher dimensional collisions, the cosmos seems to resist any interpretation that confines it within narrow boundaries. Every attempt to define an edge reveals instead a new structure beyond it, a deeper level of organization, a wider context in which the visible universe plays only a small role. The more one studies this question, the more the idea of a physical edge recedes. Instead, horizons form, not barriers, but limits within which information can travel. The cosmic horizon, defined by the age of the universe and the speed of light, marks the boundary of what can be seen. Yet the universe itself extends beyond that limit, and its structure can be inferred through indirect means. Observations of distant galaxies, measurements of background radiation, and simulations of cosmic structure formation all provide insights into regions forever hidden from direct view. The tension between visibility and existence becomes part of the mystery. Everything beyond the horizon remains unseen but not uninferred. The distribution of galaxy clusters at the limits of observation, the alignment of cosmic microwave background anisotropies, and the behavior of dark energy all provide clues about the universe beyond the visible sphere. These clues form a subtle map of what cannot be directly observed, revealing patterns that continue outward even as the light from those regions has not yet reached any observer. From another angle, quantum mechanics deepens this sense of extension. The wave functions of fields that permeate space do not stop at the boundary of the observable universe. They extend beyond, interacting only indirectly with the visible region but existing nonetheless. The inflaton field, responsible for inflation, the Higgs field that gives particles mass, and even the quantum fluctuations that shape space-time geometry all exist across the entire cosmological domain, not merely the part illuminated by ancient radiation. This continuity suggests that the universe is not a bounded object, but a field of relationships extending without interruption. Each idea expands the possible picture. Each model deepens the horizon. Each theory reveals that beyond the universe there may be structure, causality, history, and fabric that cannot be reached yet still forms part of the whole. What lies beyond is not a single concept, but a spectrum of possibilities shaped by the interplay of gravity, quantum fields, geometry, and time. And all of these possibilities, grounded in real research and observation, grow from a simple fact. The observable universe is limited not by the extent of reality, but by the time light has had to travel. The horizon is temporary. With each passing year, new layers of the cosmos drift into view, though the expansion of space constantly stretches distant regions beyond reach at the same time. The balance between these two processes sets the boundary between what can be seen and what remains hidden. Yet the hidden regions are no less real for being inaccessible. The cosmic horizon, though defined by the finite age of the universe, is not a fixed boundary, and this alone reshapes the meaning of what lies beyond. As the universe expands, light from increasingly distant regions has time to reach observers, gradually revealing structures that were once hidden. Yet, at the same time, the accelerating expansion driven by dark energy pushes distant galaxies away faster than light can compensate, creating a domain beyond which no information will ever arrive. This interplay of revelation and retreat gives the horizon a dynamic quality. It recedes and advances in conceptual space even as it remains physically unreachable. Deep surveys, such as those conducted by the Hubble Space Telescope and now the James Webb Space Telescope, capture light from galaxies that existed when the universe was only a few 100 million years old. These galaxies appear small, irregular, and intensely active in star formation, reflecting the chaotic conditions of an early cosmos. But even these faint smudges on the edge of detection are not objects at the universe's limit. They are simply the oldest sources whose light has had time to arrive. Beyond them lie untold billions of galaxies, whose photons are still stretching across an expanding sea, many of which will never reach any observer because the space between them and every point of view grows too quickly. This observable boundary forms a sphere around every observer, but it is not a wall. It is more like the fading edge of a lantern's glow in a fog of infinite depth. The regions beyond it remain part of the same physical structure, shaped by the same laws and formed through the same processes. They differ only in their inaccessibility. If one could stand on a distant galaxy at the edge of our view and look outward from there, an entirely new horizon would emerge, filled with galaxies we will never see. Reality continues far beyond what any single vantage point can reveal. This understanding becomes more concrete when viewed through the lens of general relativity. Space-time is not a container that holds the universe, it is the universe itself. Distances, durations, and boundaries arise from relationships within space-time, rather than from an external frame. Asking what lies beyond the universe therefore carries a hidden assumption that there is an outside into which the universe is placed. But the equations describing gravity do not require such an exterior. They describe curvature, energy, and motion within the manifold of space-time without referencing any embedding space. Beyond the universe, in this strict sense, does not exist because the universe includes all points of space-time. What lies beyond is not a place but a conceptual extension of regions that cannot be seen. Yet this interpretation, elegant as it is, only applies to models in which the universe is a single connected structure. It does not limit the possibility of more extensive frameworks in which our cosmic manifold is one of many. Theories inspired by string theory, for instance, suggest that the familiar dimensions of space may occupy a brane floating in a higher dimensional space called the bulk. In this context, the universe is not everything. It is simply the three-dimensional surface on which known physics unfolds. Beyond it may lie additional spatial dimensions, each with their own branes, each potentially hosting their own physical laws. This idea gained traction partly because higher dimensional models can elegantly address long-standing puzzles in particle physics and cosmology. They can explain why gravity appears so much weaker than other forces by allowing gravitational influence to leak into higher dimensions. They can provide mechanisms for cosmic inflation by describing how branes move and interact within the bulk. Some versions even predict that gravitational waves might reveal subtle signals from these interactions, though such evidence remains speculative. If such a model reflects reality, then beyond the universe is a literal extension into additional dimensions. Not empty space, but a geometric domain that cannot be entered by ordinary matter or radiation. Our universe becomes a vast but finite sheet floating in an ocean of higher dimensional geometry. What lies beyond its edge is not a void, but a region where the coordinates familiar to physics no longer apply. The structure could extend indefinitely or fold back upon itself, forming configurations that challenge conventional intuition. The cyclic version of the ekpyrotic model offers a different perspective. Here, the universe, as observed, emerges from repeated collisions between branes in higher dimensional space. Each collision releases energy, producing a new cosmic cycle with expanding space, cooling matter, and the long formation of galaxies. After immense timescales, the branes again approach each other, initiating another cycle. In this vision, the universe has no ultimate beginning or end in time. What lies beyond the current universe is another universe in the past and another yet to come, each linked by dynamics invisible to four-dimensional observers. This model suggests that remnants or faint hints of earlier cycles might appear in the cosmic microwave background. Some researchers have examined anomalies such as the unusually cold patch known as the cold spot, or slight alignments in the large-scale temperature multipoles. While these features might simply be statistical fluctuations, they could also represent imprints from a pre-existing cosmic structure. If ever confirmed, they would reveal a profound truth: that beyond the earliest observable epoch lies another universe whose history preceded ours. A different line of inquiry comes from quantum cosmology, which attempts to unify general relativity with quantum mechanics. In some approaches, the wave function of the universe describes all possible configurations of space-time and matter. The no-boundary proposal of Stephen Hawking and James Hartley posits that the universe does not originate from a singular point, but emerges smoothly from a region where time loses its classical meaning. In such a model, asking what came before the universe is analogous to asking what lies south of the South Pole. Time itself curves in a way that removes the need for a temporal boundary. In this view, beyond the universe exists only in the sense of the mathematical structures that describe its earliest quantum state. That state does not resemble space or time as understood now, nor does it belong to an earlier era. It is simply the condition from which classical space-time emerges. Nothing precedes it because before is not defined in that regime. Yet this is not a metaphysical claim. It is the result of applying quantum rules to gravitational systems and allowing geometry itself to behave like a quantum variable. While these theoretical approaches vary, they converge on a shared insight. The observable universe is only a fragment of a deeper and more expansive reality. Whether that reality is spatially infinite, cyclic in time, embedded in higher dimensions, or part of an eternally growing inflationary landscape, it extends beyond what can ever be measured directly. The limits of observation carve out only a small region in a fabric that stretches outward in forms hinted at by mathematics, supported by data, and refined by the ongoing efforts of cosmologists seeking coherence in the vastness. Observational studies of large-scale structure reinforce this sense of extension. Surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument map millions of galaxies, revealing a cosmic web of filaments, walls, and voids stretching across billions of light years. The patterns appear consistent at every scale that can be observed. There is no indication that the structure will suddenly end just beyond the horizon. Instead, all available models suggest continuity. The forces that shaped the cosmic web operate everywhere. Gravity pulls matter into clusters. Dark matter sculpts invisible scaffolding, and dark energy drives expansion. These processes have no apparent boundary. Even the presence of dark energy points toward a future in which the observable universe shrinks in a relative sense. As expansion accelerates, more galaxies will drift beyond the horizon. The visible cosmos will eventually consist only of the structures gravitationally bound to the local group. Everything else will fade into darkness, not because it ceases to exist, but because light can no longer span the growing gulf. What lies beyond, in the deep future, will be a universe full of galaxies carried away on currents of expansion that no observer can reverse. Through all of these perspectives, one fact becomes clear. The universe resists confinement. At every scale, it expands outward in possibility, whether through geometry, quantum processes, higher dimensional structures, or the accumulation of time. What lies beyond is not a simple answer, but a collection of scientifically grounded possibilities, each offering a different window into a realm forever hidden, yet undeniably real. Each of these models, whether drawn from classical geometry, inflationary dynamics, higher dimensional physics, or quantum cosmology, extends your sense of reality outward, but the expansion does not stop there. The frontier of what lies beyond the universe now stretches into areas shaped not only by observations and equations, but by the deep logic of physical law. The very structure of the laws themselves may imply the existence of regions outside the observable cosmos, not through direct prediction, but through the necessity of completeness. If the universe were confined entirely to what can be seen, certain symmetries, conservation principles, and energy distributions would appear inexplicably truncated. The consistency of known physics subtly hints at continuation. One clear example comes from the distribution of matter and the cosmic web mapped by large redshift surveys. Every region observed follows the same statistical properties. Clusters form at intersections of filaments, voids expand slowly over billions of years, and the web extends in repeating patterns without disruption. Such uniformity suggests that the structure did not abruptly end just beyond the visible volume. The initial conditions that gave rise to this web must have been imprinted on scales far larger than anything detectable. This continuity is one of the quiet signatures pointing to a universe whose boundaries exceed observation rather than ending at the edge of sight. Another clue arises from the near uniformity of the cosmic microwave background. The temperature across the sky differs by only tiny fractions of a degree. Yet, regions on opposite sides of the sky have not had enough time to exchange information since the beginning of expansion. The only widely accepted explanation is that those regions were once in close contact before inflation stretched them apart. This implies that the observable universe is a mere patch of a broader region that was once more tightly connected. Beyond the visible sphere lies territory that once shared the same primordial interactions, shaped by the same processes before inflation expanded them beyond mutual reach. As one traces these clues further outward, the idea emerges that the universe possesses a kind of large-scale coherence that observation can sample only partially. The distribution of galaxies, the shape of the cosmic microwave background power spectrum, and the coherence of baryon acoustic oscillations all hint at processes that acted across enormous stretches of space. This points to a cosmos that extends far beyond what any observer will ever see, not as speculation, but as the logical consequence of physical rules operating consistently across scales. At the same time, the possibility remains that the universe is not infinite, but finite in ways subtle enough to evade detection. If the universe possesses a non-trivial topology, the characteristic scale of its shape could be many times larger than the observable region. Even if space is finite, that finiteness might lie at lengths unreachable by any measurement. In such a case, what lies beyond the observable universe is more space that eventually loops back on itself, creating a vast but closed environment in which no boundary exists, only a continuing geometry. The absence of repeated patterns in cosmic microwave background data does not eliminate this possibility. It merely indicates that if repetition exists, it lies beyond the current horizon. This tension between infinite and finite space reflects a deeper truth, that the size of the universe cannot be inferred solely from observation, but must be combined with theoretical insight. General relativity accommodates a range of scenarios, from infinite flat spaces to closed spherical ones, from hyperbolic geometries to complex manifolds that defy simple description. Observations constrain only a small region within a sea of possible shapes, leaving the global structure unknown. In this uncertainty lies the potential for realities extending beyond anything visible. Another dimension of the question arises when considering the behavior of energy fields that govern the universe's evolution. The inflaton field responsible for early inflation, the dark energy driving current acceleration, and the quantum fields permeating space all extend beyond observational boundaries. their behavior is not limited to the region from which light has reached us. These fields possess values and dynamics throughout the entire cosmic domain, known or unknown. If these fields shaped the early universe, their influence must extend into regions still hidden. Their continuity ensures that physics remains consistent across the horizon and beyond, reinforcing the idea that the unseen portions of the universe are not separate realms, but natural extensions of the same physical environment. The study of gravitational waves offers yet another possible window into the beyond. Observatories such as LIGO and Virgo have already detected ripples in spacetime caused by merging black holes and neutron stars. Future detectors, including the planned LISA mission, aim to detect lower frequency waves that could originate from processes occurring on scales far larger than those currently observed. If primordial gravitational waves from the earliest moments of the universe are detected, they might reveal information about regions beyond the observable sphere. These waves could carry imprints from inflation itself, reflecting conditions across the entire inflating domain. In that case, the beyond becomes accessible not through light but through vibrations of space-time that traverse the universe in ways light cannot. Another possibility comes from the study of cosmic variance. The largest scale features of the cosmic microwave background appear slightly anomalous, such as the low power in the quadrupole mode and certain hemispherical asymmetries. These anomalies might be statistical noise or artifacts of measurement, but they could also hint at structures larger than the observable universe. If the universe possesses gradients or directional features on scales far beyond what can be seen, those features could imprint subtle signatures on the visible portion. This would mean that the beyond is not uniform, but possesses characteristics that influence the observable region indirectly. Such features would suggest that the universe has structure on scales larger than the cosmic horizon, extending the concept of beyond into regions that shape the visible cosmos without revealing themselves directly. In addition to these scientific considerations, the question of what lies beyond the universe touches on the nature of time itself. In many cosmological models, time emerges from the relationships between events within the space-time manifold. If the universe began in a highly uniform state and expanded into its current structure, then time has meaning only within this expanding region. Asking what happened before or outside that region requires extending the concept of time beyond its definition. In the no-boundary model, time curves into a state where it loses classical meaning, removing the need for a before. Yet in cyclic or bouncing models, time stretches backward indefinitely, carrying the universe through phases of contraction and expansion. In that framework, the beyond becomes an earlier era rather than an external space. These differing perspectives highlight the multifaceted nature of the question. Beyond the universe could refer to regions outside the observable horizon, dimensions beyond the familiar ones, earlier cycles of cosmic evolution, or structures emerging from the laws that govern spacetime. Each interpretation carries scientific weight, reflecting genuine inquiries into the nature of reality. As the exploration continues, the role of dark matter and dark energy becomes increasingly significant. Dark matter shapes the cosmic web through its gravitational influence, forming halos in which galaxies coalesce and evolve. Its distribution extends far beyond what can be directly observed. If the universe continues far beyond the current horizon, dark matter must also fill those regions, creating structures consistent with the universal web pattern. Dark energy, constituting the majority, of the universe's energy content affects the expansion of space uniformly. If it remains constant, it will continue to drive accelerated expansion indefinitely, pushing distant galaxies farther away and expanding the horizon. Its presence across the entire observable universe implies a presence beyond it as well, affecting the dynamics of unseen regions just as it affects the visible ones. The consistency of these fields across observable space suggests that the underlying laws governing them extend beyond observation. If dark matter and dark energy behave uniformly across billions of light years, there is no reason to assume their influence ends abruptly at the horizon. What lies beyond becomes part of a larger field of dynamic processes, continuing in ways consistent with everything seen. In parallel, the study of large-scale simulations has provided insight into how the universe behaves beyond observable limits. Projects like the Millennium Simulation and Illustris have modeled billions of particles interacting under gravity, forming structures that resemble the cosmic web. These simulations extend far beyond the range of telescopes, showing how matter distributes itself when allowed to evolve over enormous volumes. They reveal that the patterns observed locally are part of a universal process that continues outward indefinitely. Even if the universe is finite, its behavior on large scales remains consistent with extension far beyond the visible region. The interplay of theory, observation, and simulation ensures that the concept of beyond remains grounded in scientific reasoning. It is not a realm of speculation detached from evidence, but a natural extension of what is known. Every line of inquiry, whether from cosmic microwave background studies, inflationary theory, quantum cosmology, or large-scale structure observations, points to the same conclusion. The observable universe is only a fraction of a larger reality. And in contemplating this, the question transforms. What lies beyond the universe is not an answer, but a direction, not a boundary, but a frontier. It is the recognition that the cosmos contains more than any vantage point can reveal, that every horizon conceals a continuation shaped by laws written into the structure of space-time. The deeper the inquiry extends into the nature of what lies beyond the universe, the more the concept itself begins to change shape. At first, it appears as a simple question of geography, an attempt to imagine an outside to all that exists. Yet, with every layer of scientific understanding, the universe reveals itself not as a discrete object, but as a process, a set of relationships, an evolving field of geometry and energy. The edge becomes a construct born of limited perspective, not a physical structure. What lies beyond becomes a realm shaped by the same laws that govern the visible cosmos, yet hidden by the constraints of light, time, and expansion. This realization sharpens when considering the role of symmetry in fundamental physics. The laws that govern particles, fields, and forces display remarkable regularities. Symmetries, such as those in the standard model of particle physics, remain consistent across all regions observed. If these symmetries arise from deeper principles, as theories like grand unification propose, then they must operate throughout the entire universe, visible or not. Their consistency across billions of light years suggests that the underlying physics is the same everywhere. Whatever lies beyond the horizon is governed by the same foundational rules, even if the details of structure differ due to differing initial conditions or quantum variations during inflation. Grand unified theories propose that the known forces emerged from a single interaction at extremely high energies. If such a unification occurred in the early universe, then all regions must have passed through the same phase transition. This implies that the field responsible for symmetry breaking extends beyond observational limits. Even if particles and interactions vary in distant regions due to quantum fluctuations during inflation, the deeper mathematical structure remains uniform. The beyond becomes a continuation of the same primordial framework, unfolding in ways consistent with everything observed. This continuity contrasts with the possibility that physical constants themselves might vary across an inflationary multiverse. In certain models, the values of fundamental parameters, such as the strength of forces or the masses of particles, can differ from one inflationary pocket to another. These variations arise from the landscape of possible vacuum states predicted by some string theory models. If this is true, then beyond the observable universe could lie regions where stars form differently, where chemistry behaves with unfamiliar patterns, or where matter itself cannot assemble into structures recognizable to human intuition. These regions would remain forever disconnected from the observable universe, separated not by space as such, but by causal boundaries created by inflation. Yet the existence of such a landscape does not imply randomness. Even if physical constants vary, the rules governing how vacuum states form and evolve remain consistent. The landscape is structured by equations describing higher dimensional geometry, flux configurations, and compactification of extra dimensions. These equations determine which vacuum states are allowed and how they transition. Beyond the universe, therefore, would not be a chaotic realm but a structured space of possibilities, each governed by lawful behavior. The diversity of regions arises from the richness of the underlying mathematics rather than from disorder. Moving outward from these theoretical structures, the concept of beyond deepens when viewed through the lens of cosmic evolution. As time progresses, the observable universe undergoes changes that gradually transform the horizon. Distant galaxies recede, the cosmic microwave background cools, and the imprint of early fluctuations fades into imperceptibility. In the far future, observers would see only the remnants of the local group of galaxies, as everything else drifts beyond reach. The beyond becomes not only a spatial frontier, but a temporal one, shaped by how the universe evolves under the influence of dark energy. If dark energy remains constant, the expansion accelerates indefinitely, and distant regions disappear from view. If it varies or decays over time, the ultimate fate of the universe changes. Some models predict that dark energy could weaken, allowing gravity to slow expansion, possibly even reversing it. Others propose that dark energy could grow stronger, tearing apart galaxies, solar systems, and eventually all matter in a scenario known as the Big Rip. Each of these possibilities reshapes what lies beyond, not because the universe itself changes size, but because the causal structure shifts. What is beyond becomes inseparable from how space and time behave in the long term. The study of dark energy is still young. Observational programs such as the Dark Energy Survey, the Vera Rubin Observatory's upcoming Large Synoptic Survey Telescope, and missions aimed at mapping baryon acoustic oscillations all seek to understand the nature of this mysterious phenomenon. If dark energy's strength or behavior can be measured with greater precision, it will reveal not only the future of the observable universe, but the nature of regions beyond it. The acceleration of space governs how horizons form and evolve, meaning that the character of the beyond depends on the physics of dark energy in ways not yet fully understood. At the same time, the question of beyond is shaped by what happens at the smallest scales. Quantum mechanics reveals that vacuum is not empty, but filled with fluctuations, fields, and virtual processes that momentarily bring particles into and out of existence. These fluctuations occur everywhere, not just within the observable region. They are part of the fabric of reality. If space-time is quantized at the Planck scale, as suggested by theories of quantum gravity, then that structure must extend throughout the entire cosmic manifold. Beyond the observable universe exists the same quantum graininess that permeates the visible portion. The nature of these fluctuations influences the growth of structure, the behavior of inflation, and the formation of black holes. Their presence beyond sight ensures that the universe remains interconnected through its foundational processes. The behavior of black holes offers yet another window into this interconnectedness. Black hole thermodynamics, Hawking radiation, and the holographic principle all suggest that information in the universe may be preserved in ways not immediately obvious. The holographic principle, developed by researchers such as Gerard T. Hooft and Leonard Susskind, proposes that the information contained within a volume of space can be encoded on its boundary. Applied to cosmology, this principle raises the possibility that the observable universe itself might have a holographic description on a distant surface, linking physics within the cosmos to physics at the horizon. The beyond, in this interpretation, becomes part of a deeper structure in which the interior and boundary of the universe share fundamental relationships. This perspective gains support from studies of the anti-de Sitter spacetime and the correspondence between gravitational theories in higher dimensions and quantum field theories in lower ones. Although the universe does not appear to be anti-de Sitter in structure, the principles arising from these correspondences may still apply in modified form. If holographic descriptions can be extended to cosmological settings, then what lies beyond the observable universe could be encoded in the structure of the horizon itself. The beyond would not be accessible, but would nonetheless play a role in shaping the information content of the observable cosmos. Meanwhile, the study of early universe cosmology through measurements of primordial abundances provides further clues. The ratios of light elements such as hydrogen, helium, and lithium formed during the first few minutes after the Big Bang match predictions from Big Bang nucleosynthesis, confirming that the early universe was hot and dense everywhere. This uniform condition must have extended beyond the visible region because nucleosynthesis requires specific temperature and density conditions across large scales. Therefore, beyond the observable universe existed the same primordial plasma, undergoing the same nuclear processes. The consistency of these abundances implies continuity across unseen regions. Beyond these physical considerations lies another dimension of inquiry, one rooted in the nature of measurement itself. Cosmology is constrained by the fact that observers occupy a single location and can only see a finite region of space. This limitation creates what is known as cosmic variance, the unavoidable uncertainty that arises when only one realization of the universe can be observed. If the universe contains structures or variations on extremely large scales, these may never be distinguishable from random fluctuations in the observable region. What lies beyond may include features that subtly influence the visible universe, yet cannot be disentangled from chance due to the limits of observation. This limitation does not reduce the reality of the beyond, but underscores the importance of theoretical frameworks in interpreting what is observed. Because the cosmic horizon hides vast regions of space, theories must extend beyond direct measurement and use principles such as symmetry, causality, and consistency to infer the structure of the unseen. This approach mirrors how physicists infer the presence of dark matter from its gravitational effects rather than direct detection. The unseen shapes the seen, even when inaccessible. As these ideas accumulate, the notion of beyond evolves from a single question into a tapestry of interconnected possibilities. It becomes clear that the universe is not bounded by the horizon, but continues in ways consistent with all known science. Even the possibility of multiple universes, suggested by inflationary theory and certain interpretations of quantum mechanics, does not contradict observation. Instead, it emerges naturally from attempts to explain why the universe possesses the properties it does. In these interpretations, the beyond includes regions with different histories, different conditions, and possibly different laws, all existing within a grander totality of reality. The interplay between these models enriches the question rather than diluting it. Each perspective brings out a new layer of understanding, showing that the universe is both deeply structured and profoundly extensive. What lies beyond the observable region may be more universe, earlier cycles of existence, higher dimensions, or other manifestations of cosmic evolution. The question remains open not because it lacks answers, but because it touches the limits of what can ever be known from within. As these models settle into place, a broader realization emerges. The question of beyond is not limited by the observable universe, nor by the classical picture of space-time, nor even by the boundaries set by human intuition. It spans multiple layers of reality, each informed by rigorous scientific investigation, each expanding the conceptual landscape farther than the horizon allows the eye to see. The universe becomes not a single container, but a vast, interconnected structure whose depth cannot be captured by ordinary language. What lies beyond becomes a question with several valid interpretations, each shedding light on a different facet of cosmic truth. One of the most revealing approaches to this question involves considering how the earliest events in the universe set conditions that still influence observable structures today. The theory of cosmic inflation suggests that quantum fluctuations in an inflating field were stretched across enormous distances, creating density variations that later evolved into the galaxies and clusters seen in large-scale surveys. These fluctuations did not start only within the observable region. They originated across an inflating space so large that only a fraction of its patterns are now visible. Their distribution indicates a process that operated uniformly on scales far greater than anything observable. This uniformity points toward a continuation of the same physical domain beyond the horizon, governed by identical mechanisms. Cosmic inflation also provides clues about the possibility of multiple universes. If inflation is eternal, then space as a whole is a patchwork of regions where inflation has ended and regions where it continues. Each non-inflating region becomes a universe with its own thermal history, while the surrounding space remains in a high-energy state. This ongoing process leads to a multiverse structure, not through speculation, but through the natural consequences of inflationary dynamics. Researchers studying the mathematical landscape of inflation have found that eternal inflation is difficult to avoid unless specific conditions are imposed. Thus, beyond the observable universe may lie an uncountable number of other regions, each isolated by expansion, each containing its own structures, and each forever beyond communication. The possibility of such a multiverse changes the meaning of beyond. Instead of suggesting an outside to everything, it points to a broader system in which the observable universe is one branch of a larger tree. The branches grow independently, shaped by initial fluctuations, quantum uncertainties, and variations in the inflaton field. They do not interact once separated, but they share a common origin in the physics that governs inflation. In this sense, beyond the universe may be another universe emerging from the same underlying process, far removed but fundamentally related. Yet, even this picture only touches one dimension of the question. General relativity allows for solutions in which the universe is part of a larger manifold with additional directions inaccessible to ordinary matter. These directions might be compactified, curled up at scales too small to detect, or extended, forming geometries that shape the behavior of forces and particles. In theories with extra dimensions, the observable universe becomes a lower dimensional surface within a higher dimensional environment. This setting changes how gravity behaves at small scales and may offer explanations for the hierarchy of forces. If matter and radiation are confined to a three-dimensional brane while gravity extends into the bulk, then the beyond in this scenario includes all the regions where these extra-dimensional directions unfold. This idea is not merely theoretical speculation. Experiments at particle accelerators, such as those conducted at the Large Hadron Collider, search for evidence of extra dimensions through deviations in particle scattering or missing energy signatures that could indicate gravitational leakage into higher dimensional space. While no such signatures have been found so far, the search continues because the theoretical motivations for extra dimensions remain strong. Their presence could unify forces, explain the weakness of gravity relative to other interactions, and provide fertile ground for models of cosmic evolution. If extra dimensions do exist, then beyond the universe is not empty space but an expanded geometric reality woven into the structure of existence. Another path into the question emerges from the study of quantum entanglement and the geometry of spacetime. Research in quantum gravity has revealed deep connections between entanglement and the shape of spacetime. Some approaches propose that spacetime itself arises from patterns of entanglement in an underlying quantum system. In these models, the geometry of the universe is not fundamental but emergent, shaped by the relationships between quantum degrees of freedom. If this is correct, then beyond the universe becomes a question of what lies outside the emergent spacetime description, in the deeper quantum substrate from which spacetime arises. This substrate may not resemble space or time at all, but it forms the foundation of everything that can be observed. In such models, the universe does not have an outside in the conventional sense. Instead, the beyond refers to levels of description beneath spacetime, where geometry dissolves and only quantum information remains. The familiar notions of inside and outside lose meaning. The universe becomes a manifestation of deeper principles that operate without reference to spatial extension. What lies beyond is the structure that gives rise to spacetime itself, the blueprint of reality that remains hidden behind the classical world. These ideas connect with the holographic principle, which suggests that the information contained within a region of space can be encoded on its boundary surface. Applied to the universe, this principle implies that the entire observable region, with all its galaxies and structure, might correspond to information stored on a distant boundary. This does not mean that the universe is an illusion, but rather that geometry and matter arise from underlying quantum relationships encoded in ways not yet fully understood. If the universe is holographic in this sense, then beyond the observable universe is not a physical extension, but additional layers of encoded information that define the structure of space. The horizon becomes not a limit of existence, but a limit of accessible information. This perspective shifts the conversation from physical geography to the nature of information itself. If reality is fundamentally informational, then what lies beyond is whatever information has not yet been revealed by the evolution of space-time. The universe becomes a dynamic system in which new regions come into view as light travels across expanding space, while other regions slip beyond reach as expansion accelerates. What lies beyond at any moment reflects the interplay between information, geometry, and time. The influence of cosmic topology provides yet another layer. Some models propose that the universe may possess a topology in which space wraps around itself in intricate ways. If this is true, then beyond the observable universe could be another region of the same space viewed from a different angle, a reflection of the universe caused by its global shape. Studies of cosmic microwave background anisotropies have probed this possibility, searching for repeating patterns that might reveal a finite but edgeless topology. While no definitive signatures have been found, the constraints are not tight enough to rule out many possible configurations. The global shape of the universe remains unknown, and space could wrap around itself on scales far larger than the horizon. If so, beyond the universe is simply more of the same space repeating at scales unreachable by light. Further insight comes from the study of gravitational lensing. Massive objects bend the paths of light, distorting images of galaxies behind them. Surveys that map these distortions reveal the distribution of dark matter and the geometry of space on large scales. These maps extend the understanding of cosmic structure beyond regions directly observable, providing indirect evidence for the continuation of matter and energy into unseen domains. Although lensing cannot reveal what lies infinitely far away, it shows that the distribution of matter follows predictable patterns that extend beyond any data set. This reinforces the idea that the universe does not abruptly end but continues according to the same rules. Black holes add still another perspective to the question. Their event horizons mark regions from which no information can escape. The universe has its own horizon, similar in some respects, created by the accelerating expansion of space. Just as nothing inside a black hole's event horizon can communicate with the outside, regions beyond the cosmic horizon can never send signals inward. Yet black holes do not imply the end of space-time within them. They represent transitions to regions described by general relativity that remain hidden. By analogy, the cosmic horizon does not signify the end of the universe but the boundary of visibility. What lies beyond is a region of space-time unaffected by the limitation imposed by light travel time. The universe may extend indefinitely beyond this horizon, shaped by processes identical to those within it. As one continues exploring these layers, the question begins to feel less like a search for a boundary, and more like a journey through the logical consequences of physical law. At every level, the universe suggests continuation. Whether through uniformity of cosmic structure, predictions of inflation, behavior of gravitational fields, or quantum descriptions of space-time. Each line of evidence points toward a cosmos that expands far beyond the horizon. The beyond exists not as a separate realm, but as the natural extension of everything that is. Even the nature of cosmic time contributes to this picture. Time does not unfold identically for all observers. Regions moving away at high speeds effectively experience different histories from those nearby. As one peers farther into the universe, one also looks backward in time, seeing younger regions. Beyond the horizon lie regions whose light has not yet reached any observer because they are too young or too distant. They are not separate universes, but newborn parts of the same universe, still unfolding their structures in ways that remain hidden. These regions will never become visible because expansion outpaces the travel time of light, but they remain parts of the cosmic whole. In this sense, the beyond becomes a mixture of different eras of cosmic history coexisting across the vastness of space. Some regions appear as they were billions of years ago, others as they are now, and still others remain forever in the future relative to any observer. Time and space weave into a single fabric where distance corresponds to epochs and horizons correspond to the limits of information. The beyond becomes not a place but a time frame, a region whose history cannot interact with the visible universe. Through all these perspectives, one finds a common thread. The question of what lies beyond is fundamentally connected to the nature of the universe itself, not to an external container or a boundary. The universe may be infinite in extent, finite but unbounded, part of a larger inflationary structure, embedded within higher dimensions, or emerging from a deeper quantum reality. Each possibility expands the horizon of understanding, showing that beyond the universe lies more structure, more geometry, more history, and more laws than the visible world can reveal. In contemplating these vast possibilities, the question of what lies beyond the universe gradually transforms into a deeper inquiry about the nature of knowledge itself. Every model, every observation, every theoretical framework extends the boundary of understanding outward, yet none remove the inherent limitations imposed by the speed of light and the age of cosmic expansion. Beyond the universe becomes an exploration not only of space and time, but of what it means for something to exist beyond direct observation. Science, through careful reasoning and mathematical structure, extends sight into the unseen, building bridges of inference toward realms forever beyond physical reach. A compelling illustration of this arises from the study of cosmic isotropy, the principle that the universe appears the same in all directions. Observations of the cosmic microwave background show remarkable uniformity, with only small fluctuations superimposed on an otherwise smooth temperature field. This uniformity suggests that the early universe was in a near equilibrium state across vast regions before inflation began. For such equilibrium to exist, those regions must once have been close enough to interact, exchanging heat and information. Yet these same regions now lie far beyond each other's horizons, unable to communicate in the present era. Their former unity implies a larger story in which the visible universe is only a fraction of a broader interconnected past. What lies beyond is the continuation of that early equilibrium, once intertwined with what is now observable. This interpretation gains strength when considering the detailed structure of those fluctuations. The distribution of hot and cold patches follows a nearly perfect Gaussian pattern, consistent with quantum fluctuations amplified by inflation. The fact that fluctuations on such large scales remain coherent suggests that inflation stretched initial quantum features far beyond the observable universe. if inflation lasted longer than the minimum needed to explain current observations. As most models predict, then the universe must extend trillions of times beyond the visible horizon. These regions, though permanently hidden, shaped the conditions of the universe's earliest moments, and thus played a role in determining its present-day structure. Further evidence comes from the study of primordial density waves. These acoustic oscillations, imprinted on the distribution of galaxies, reveal how matter clustered in the early universe. The scale of these oscillations reflects the conditions that must have existed uniformly across regions now separated by unbridgeable distances. Their presence suggests a cosmic coherence larger than the observable region, another sign that the beyond is not a separate realm, but a continuation of the same environment that shaped the visible universe. Venturing deeper, the concept of beyond acquires another dimension when considering the behavior of black holes. In general relativity, black holes represent regions of space-time where curvature becomes so intense that no signal can escape once it crosses the event horizon. The interior of a black hole does not cease to exist. It simply becomes inaccessible to outside observers. Similarly, the cosmic horizon does not mark the end of space-time, but the limit of what can be accessed. Everything beyond the horizon exists in a causal shadow, influencing the visible universe only indirectly through early conditions and large-scale structure. Yet, in some models of black hole physics, horizons possess holographic properties. If the cosmic horizon behaves analogously, then it may encode information about regions beyond it. This idea is speculative but grounded in serious research. It suggests a profound link between observable and unobservable regions, implying that information about the beyond may be woven subtly into the structure of the visible universe. Even if direct access is impossible, indirect imprints may remain, hidden in the fabric of cosmic background radiation or gravitational wave signatures. The interplay between local and global features becomes especially important when considering topology. If the universe has a non-trivial global shape, the patterns of cosmic microwave background fluctuations should reflect this structure. Searches for matched circles in the sky, which would indicate a repeating topology, have so far yielded no confirmed results. But the lack of detection does not rule out the possibility. The size of a topological feature might simply exceed the observable region. In that case, the beyond contains repeated structures of the same cosmic manifold extending farther than light can travel. The universe could be finite yet seamlessly connected without the need for boundaries. Concepts like these show that the beyond is shaped less by abrupt endings and more by smooth continuations of processes that operate across vast scales. Inflation, quantum fluctuations, general relativity, and large-scale structure formation all point to a universe that extends far beyond the visible sphere. The continuity of these processes offers glimpses into the unseen, suggesting that the regions beyond are governed by the same fundamental principles, even if their specific details differ. Another layer of the question emerges when considering how physical constants influence the formation of structure. In many inflationary multiverse models, slight variations in vacuum energy or the strength of forces can result in universes with dramatically different properties. Some pocket universes might expand too quickly for galaxies to form. Others might collapse before stars ignite. Still, others might possess different chemistry, where atoms fail to assemble into stable molecules. These variations, if they exist, highlight the possibility that beyond the observable universe lies a landscape filled with regions governed by different parameters. Yet these differences remain structured within a larger theoretical framework. They do not imply chaos, but rather a diversity arising from lawful behavior in a space of possible vacuum states. The beyond becomes a multidimensional terrain shaped by fields and geometries that determine how universes emerge and evolve. This interpretation intersects with anthropic reasoning, which explores why the observable universe possesses properties conducive to life. If countless regions exist with varying constants, only those where stable structures form can host observers. While this reasoning remains debated, it provides a potential explanation for why the universe exhibits fine-tuned values. The beyond would include regions where conditions differ too greatly for complex structures to form, yet their existence is not excluded by physical law. At the same time, the search for fundamental theory continues. Efforts to combine quantum mechanics with general relativity aim to produce a unified view of the universe at all scales. Approaches like loop quantum gravity, string theory, and causal dynamical triangulations attempt to describe spacetime's texture at its smallest units. These theories suggest that spacetime is not smooth, but composed of discrete building blocks. If so, these structures extend throughout the universe, visible or not. Beyond the observable region lies a spacetime constructed from the same fundamental units, woven into the same fabric that shapes the visible cosmos. This discrete structure may influence cosmic evolution in subtle ways. Quantum gravity effects could prevent singularities, produce bounces in cosmological cycles, or alter the behavior of black holes. If these effects occur globally, they must operate not only within the visible universe, but across the entire cosmic domain. The beyond becomes part of an evolving sequence of cosmic phases, linked through transitions that shape the universe's long-term history. Furthermore, models of cyclic cosmology propose that the universe undergoes repeating expansions and contractions. Each cycle might erase most of the previous cycle's structure, while leaving behind subtle imprints in the conditions of the next. If the universe behaves cyclically, then the beyond includes entire epochs of cosmic history preceding the Big Bang. These epochs remain hidden by the bounce or collision that initiated the current expansion, but may have influenced its properties. The beyond becomes not a spatial extension but a temporal lineage stretching across cycles of unimaginable length. This possibility gains interest from anomalies in the cosmic microwave background. Some researchers have identified concentric circles of unusually low temperature variance, proposing that they might reflect interactions between supermassive black holes from a previous cosmic era. While this interpretation remains speculative, the mere possibility shows how observations could reveal information about epochs beyond the conventional beginning. Another intriguing avenue comes from quantum decoherence and the many worlds interpretation of quantum mechanics. In this view, every quantum event with multiple possible outcomes produces branching universes that evolve independently. These branches are not spatially separated, but represent distinct histories unfolding within the same mathematical structure. The beyond, in this context, is not a region of space, but a divergence of possibilities. Each branch evolves according to its own history, yet all branches share a common origin in the universal wave function. This interpretation raises profound questions about the nature of reality. If all possible outcomes occur in separate branches, then beyond the universe in this sense refers to the vast ensemble of parallel histories coexisting with the one observed. These histories do not interact, but they are part of the total structure described by quantum mechanics. The universe becomes a single manifestation among countless others, each exploring different versions of events. While these interpretations remain theoretical, they highlight the complexity of defining what lies beyond the universe. The beyond can refer to regions outside the observable sphere, dimensions outside familiar space, epochs before the Big Bang, other universes produced by inflation, or branches created by quantum processes. Each interpretation stems from serious scientific inquiry, not speculation detached from evidence. These ideas reflect attempts to unify observations, mathematical consistency, and theoretical coherence into a comprehensive view of the cosmos. Even the study of high-energy physics contributes to understanding the beyond. Particle accelerators probe conditions that existed fractions of a second after the Big Bang, revealing interactions that shaped the early universe. If new particles or forces are discovered, they could provide insight into the universe's fundamental structure, which extends beyond the visible region. Some theories predict particles that interact only gravitationally or through extremely weak forces. These particles may fill space beyond the horizon, influencing the universe's behavior on large scales. Cosmic neutrinos, relics from the first seconds of the universe, also offer a glimpse into the beyond. Although difficult to detect, they permeate space, including regions beyond the horizon. Their distribution reflects conditions that existed everywhere at early times. Detecting them would open a new window into the unseen universe. Through all these avenues, one finds that the beyond is not empty or undefined. It is structured by physical laws, shaped by cosmic history, influenced by fields and particles, and governed by geometry. The visible universe is a small portion of a reality that extends across dimensions, scales, and epochs. Through each of these perspectives, a broader principle starts to emerge, one that reflects the cumulative insights of cosmology, quantum physics, and mathematical reasoning. The universe reveals itself not as a bounded object, but as an ever-growing horizon of understanding. With every new discovery, the boundary of the known expands while the boundary of the unknown recedes just as quickly. The concept of beyond becomes not an obstacle, but an invitation, a direction in which knowledge naturally extends. It is the recognition that the cosmos holds more structure, more depth, and more history than any finite set of observations can encompass. This vastness becomes even clearer when considering the growth of cosmic structure over billions of years. Galaxies formed from small density variations that originated in quantum fluctuations during inflation. These variations reflect conditions that existed across regions far larger than the observable universe. Their distribution suggests that the same physical processes operated uniformly everywhere, shaping matter into filaments and clusters according to rules that hold throughout the cosmos. If the early universe had been different beyond the visible region, the distribution of galaxies would reveal inconsistencies across the sky. Instead, the uniformity of cosmic structure points toward an extended domain of similar conditions. This uniformity also appears in the distribution of dark matter, which forms the unseen scaffolding for galaxies. Observations of galaxy rotation curves, gravitational lensing, and large-scale structure formation reveal that dark matter behaves consistently across all regions observed. Its influence extends far beyond the reach of telescopes, shaping the universe on scales too large for direct observation. If the universe continues beyond the cosmic horizon, dark matter fills those regions as well, forming additional halos and filaments consistent with the global cosmic web. The beyond becomes a continuation of the same intricate structure mapped by surveys across billions of light years. Another clue arises from the study of dark energy, the mysterious phenomenon driving the accelerated expansion of the universe. Measurements of supernovae, baryon acoustic oscillations, and cosmic microwave background fluctuations reveal that dark energy behaves uniformly across all observed regions. Its influence must extend beyond the horizon because its effect is tied to the fabric of space-time itself. If dark energy permeates all of space, then the universe beyond the horizon expands under its influence just as the visible region does. This uniform expansion suggests that the universe continues smoothly outward, shaped by the same factors that govern everything seen. The behavior of dark energy remains one of the most intriguing aspects of modern cosmology. If it is truly constant, it will eventually stretch the universe so rapidly that distant galaxies recede faster than light can traverse the expanding space. But if dark energy evolves over time, the universe's fate could differ dramatically. Some models propose that dark energy might decay, slowing expansion and potentially reversing it. Others propose that it could grow stronger, leading to a catastrophic tearing apart of all structures. In either case, the beyond remains a region influenced by dark energy's behavior, extending far beyond what any observer can witness directly. The interplay of theory and observation also highlights another important idea: that the beyond is not simply a spatial extension but a conceptual one. For example, some cosmological models suggest that the universe may have originated from a quantum fluctuation in a timeless realm. In these interpretations, the universe emerges from a quantum state without an external time parameter. Time itself arises when the universe transitions into a classical phase. In such a view, beyond the universe refers to the quantum conditions that preceded classical spacetime, not to an external location. The beyond becomes the boundary between classical and quantum reality, where familiar notions of space and time lose their meaning. This perspective connects deeply with the approach of loop quantum cosmology, which replaces the classical singularity with a quantum bounce. In this framework, the universe contracts to a point where quantum effects dominate and then rebounds into expansion. The pre-bounce universe could have had structures, stars, galaxies, or even entirely different physical laws. These structures remain inaccessible because the bounce erases most information from the previous cycle. Yet their existence remains a possibility, grounded in the equations of quantum geometry. The beyond becomes a time before the Big Bang, a period hidden from observation, but perhaps still reflected in subtle patterns in cosmic background radiation. Such bounce models challenge the traditional view of cosmic origin. Instead of a universe arising from nothing, they suggest a continuous process in which one phase leads to another. The beyond becomes part of an ongoing sequence of cosmic transitions. The observable universe would then be one moment in a vast timeline extending in both directions, with each era separated by quantum phases that reset the fabric of space-time. This possibility profoundly alters the meaning of beyond. It becomes not only a question of distance but of time, not only of location but of history. At the same time, Other cosmological frameworks propose that the universe may have multiple spatial regions connected in ways that defy intuitive understanding. For example, models of wormholes in general relativity suggest that spacetime could connect remote regions through shortcuts that bypass conventional paths. While such structures remain speculative and unsupported by observation, they demonstrate the flexibility of spacetime geometry when extended beyond familiar conditions. If wormholes exist somewhere in the universe, they could connect regions far beyond the horizon, creating links between otherwise inaccessible areas. These connections, if they exist, would challenge any simple notion of beyond, suggesting that the universe might be more interconnected than distance alone implies. Quantum entanglement further blurs the boundaries of beyond. Entangled particles remain correlated regardless of distance, suggesting that quantum information transcends classical spatial separation. Some theoretical approaches propose that spacetime geometry itself may emerge from patterns of entanglement. If so, the beyond might not be defined by spatial distance, but by the structure of quantum relationships. Regions of the universe beyond the horizon could still be connected through entanglement, even if no classical information can pass between them. This connection would not transmit signals or allow communication, but would reflect a deeper unity in the fundamental fabric of reality. These insights extend to theories of cosmic inflation that incorporate quantum fluctuations. When inflation stretches quantum fluctuations across vast scales, some fluctuations may separate regions that share a common origin. Their entanglement persists even as they drift beyond each other's horizons. This interconnectedness suggests that the beyond is not disconnected from the observable universe, but shares a quantum history with it. While these features remain theoretical, they reflect a growing recognition that spacetime may emerge from deeper principles that govern the entire cosmic domain. Another important perspective comes from simulations of cosmic structure over time. Large-scale computational models such as Illustris and Eagle simulate billions of particles under the influence of gravity, hydrodynamics, and feedback from stars and black holes. These simulations reveal how galaxies form, merge, and evolve within the cosmic web. They show that the universe's large-scale structure is statistically similar across vast distances. If the universe extends beyond the horizon, as most models predict, then it contains countless additional structures following the same patterns. The beyond becomes a continuation of the cosmic web on scales too large for light to reveal. Furthermore, the study of galaxy evolution across cosmic time reveals that star formation, chemical enrichment, and black hole growth follow patterns that repeat across different epochs. These patterns imply that the processes guiding cosmic evolution are not confined to the observable universe. They must operate in all regions where matter exists. If galaxies beyond the horizon exist, they likely follow similar evolutionary paths. This repetition of cosmic behavior reinforces the idea that the beyond is not fundamentally different from the observable region, but is governed by the same laws. At this point, the concept of beyond begins to feel less like a question and more like a comprehension of the cosmic whole. Beyond the observable universe lies more universe, shaped by the same physics yet forever hidden by the constraints of distance and time. Beyond the classical universe lies a quantum realm where space-time emerges from deeper principles. Beyond the expanding cosmos lies a landscape of regions influenced by inflationary fields and higher dimensional structures. beyond the origin lies a potential history of previous cycles or quantum states. Each of these layers adds depth without excluding the others. They coexist as interpretations rooted in real scientific inquiry, forming a multidimensional understanding of the cosmos. The beyond becomes a spectrum of possibilities, all grounded in established theories, observations, and mathematics. It is the recognition that the universe is more extensive, more ancient, and more intricate than any single perspective can grasp. As these ideas interweave, the universe begins to appear not as a single isolated structure, but as a vast, layered reality, where each level hints at the next. The observable cosmos stands as just one surface of an immense tapestry, whose threads stretch outward into regions that no telescope will ever reach, inward into quantum structures that no experiment can yet resolve, and backward into epochs that classical time cannot describe. What lies beyond becomes an unfolding of this pattern, a continual revealing of deeper order behind the visible world. The coherence of cosmic structure provides one of the most compelling indications that whatever lies beyond the horizon must share continuity with what is seen. When cosmologists measure the distribution of galaxies, they find that the universe follows a specific pattern known as the two-point correlation function. This function describes how galaxies cluster across different scales, and its shape matches predictions from inflationary models with remarkable precision. The fact that the same pattern appears across billions of light years suggests that the forces shaping it operated consistently in regions now far beyond the reach of observation. These forces include gravity, the behavior of dark matter, and the imprint of initial fluctuations. Their uniformity points toward a universe whose underlying rules extend far beyond human sight. Further evidence comes from studies of baryon acoustic oscillations, which reflect sound waves propagating through the early universe's plasma before atoms formed. These oscillations left faint imprints on both the cosmic microwave background and the distribution of galaxies. Their scale is measured with extraordinary accuracy and remains consistent across different surveys and epochs. Since these imprints were generated simultaneously across vast regions in the early universe, their consistency implies that beyond the horizon lies more territory shaped by the same primordial waves. The sound of the early universe, frozen in time, echoes across regions that light will never reach. The cosmic microwave background itself continues to provide subtle hints of patterns beyond the observable limit. While the temperature fluctuations follow predictions extremely well, certain large-scale anomalies challenge the simplest interpretations. These include slight hemispherical asymmetries and alignments known as the axis of evil, whose origins remain debated. If they arise from conditions spanning scales larger than the observable universe, then they may represent hints of structures beyond the horizon. Although the significance of these anomalies is uncertain, their presence encourages the exploration of cosmological models that include features on super-horizon scales. One of the most powerful approaches to exploring the beyond involves understanding how inflation sets initial conditions. Inflation stretches quantum fluctuations into classical perturbations that seed cosmic structure. The spectrum of these perturbations depends on the properties of the inflaton field and its potential. If inflation lasted longer than the minimal amount needed to produce the observable universe, as most models predict, then it would have expanded space to a size unimaginably larger than what can be seen. The observable region becomes just a tiny segment of a vast inflating manifold. In this scenario, the beyond is simply more universe, extending outward in a continuous flow of space-time governed by the same equations. This leads naturally to the concept of the inflationary multiverse, where inflation does not end everywhere at once. Instead, different regions exit inflation at different times, each forming its own universe with distinct properties. These universes are not separate dimensions, but separate domains of a larger inflating space-time. Their separation arises because the expansion between them occurs faster than signals can traverse, making each region causally isolated. In this framework, beyond the eye observable universe may lie other regions that cooled into their own galaxies, stars, and potentially complex structures. While these regions remain forever inaccessible, their existence follows from the same physics that explains the observed structure of the universe. The possibility of multiple universes gains further grounding from certain interpretations of quantum mechanics. In the many worlds interpretation, every quantum event results in branching realities where all possible outcomes occur. While these branches do not interact, they coexist as parts of a larger quantum structure. If this interpretation is correct, then beyond the universe refers also to these parallel histories, existing not in distant space but in the underlying mathematical description of quantum evolution. The beyond expands from spatial and temporal domains into the realm of possibility itself. Yet the beyond is not only about what exists in distant regions or alternative histories. It also concerns what lies beneath the surface of space-time. Advances in quantum gravity suggest that space-time may not be fundamental. Instead, it may emerge from more basic entities, such as spin networks in loop quantum gravity or extended objects in string theory. If space-time is emergent, then the beyond includes the underlying structure from which space and time arise. This structure could contain more dimensions, different symmetries, or entirely new types of entities. The visible universe becomes a manifestation of rules that operate at a deeper level, hidden from direct observation. Some models propose that entanglement plays a key role in the emergence of space-time. In these models, the geometry of space reflects patterns of quantum entanglement among fundamental degrees of freedom. If so, then the beyond includes entanglement patterns extending across the entire universe, shaping geometry even in regions beyond the causal horizon. These patterns connect the observable region to realms that cannot be accessed directly, suggesting that the boundaries of space are reflections of information flow rather than absolute divisions. Research on holography reinforces this view. The holographic principle implies that the maximum amount of information stored within a region of space is proportional not to its volume, but to the area of its boundary. This relationship suggests that the fundamental description of the universe may reside on a distant boundary, with the interior emerging from boundary data. If this principle applies to cosmology, then the observable universe may be encoded on a cosmic horizon. In this sense, the beyond includes the degrees of freedom that give rise to the visible cosmos, existing not in space but in an underlying informational structure. These considerations show that the beyond can take many forms: spatial extensions, earlier cosmic phases, alternate inflationary regions, higher dimensions, emergent structures, or parallel quantum histories. Each interpretation expands the notion of what is possible, revealing that the limits of observation do not constrain the limits of existence. the universe remains larger in concept than in any view a single observer can access. This becomes especially clear when considering the long-term future of the cosmos. As expansion accelerates, distant regions recede faster than light can travel. Over time, galaxies beyond the local group will disappear from view, leaving behind a universe that appears increasingly empty. Even within the observable region, features fade as the cosmic microwave background cools and structures evolve. Future observers may find themselves in a cosmos that seems isolated, unaware of the vast structures once visible. The beyond becomes silent, not because it ceases to exist, but because the information that once connected observers to distant regions becomes irrevocably lost. In this distant future, the concept of beyond may acquire a different meaning. Instead of referring to regions beyond the horizon, it may refer to a deeper understanding of past epochs. Observers may reconstruct the early universe from fossil evidence left in cosmic structures, just as modern scientists reconstruct early cosmic history from the microwave background. This reconstruction may reveal indications of processes that occurred before the observable universe formed. Thus, the beyond remains a frontier not only in space but in time, stretching into both the future and the past. Another layer of inquiry arises from considering the possibility that the universe may experience phases of accelerated and decelerated expansion. If dark energy changes over time, the universe might pass through different eras, each governed by different dominant forces. These transitions could create new horizons, reveal new regions, or conceal parts of the universe that were once observable. The beyond becomes dynamic, reshaped by the behavior of cosmic energy. Future cosmological observations may reveal subtle changes in the expansion rate that indicate a shift in the nature of dark energy. If such changes occur, they could open up new perspectives on what lies beyond. The question also gains depth through comparisons of cosmic measurements from different observatories. The slight discrepancies between measurements of the expansion rate from the early universe and those from nearby structures may indicate unknown physics at work. If this tension reflects new fundamental processes, they must operate throughout the universe, not only within the observable region. The beyond becomes part of a system governed by these new processes, whether they involve evolving dark energy, modifications to gravity, or the presence of new types of particles. Each possibility extends the known universe into a larger conceptual framework. Physics also explores the beyond through the study of black hole interiors, where space-time curvature grows extreme. Some theories propose that black hole interiors may connect to other regions of space-time, potentially forming bridges to distant areas or entirely different universes. While these ideas remain speculative, they illustrate the flexibility of space-time geometry in extreme conditions. If such connections exist, the beyond becomes a network of pathways linking different regions, albeit in ways hidden from external view. Even if black hole interiors do not provide physical connections, their behavior teaches much about the limits of space-time. The information paradox, for example, challenges the assumption that information falling into a black hole is lost forever. Resolutions of this paradox often involve holographic principles or modifications to the structure of space-time at small scales. These insights translate directly to cosmology, suggesting that the universe's horizon may also encode information in ways not yet understood. The beyond becomes a domain whose influence is encoded subtly in the structure of observable space. Nothing in modern cosmology indicates that the universe simply ends. Every model that successfully describes observations implies continuation, whether in space, time, or a deeper level of structure. The beyond is not an abrupt ceiling, but a realm shaped by the same laws that govern everything seen. It includes regions of space beyond the horizon, regions of time before the Big Bang, regions of mathematics underlying space-time, and regions of possibility described by quantum theory. As these ideas accumulate, the universe appears increasingly vast and layered, with the observable region forming only one chapter in a much larger narrative. The beyond is not a mystery to be solved once, but a direction in which thought can always continue. It reflects the limitless potential of scientific inquiry, the realization that the cosmos offers more than any single perspective can reveal. And, as these possibilities settle together, something quiet rises through all of them, something steady and enduring. Every theory, every observation, every simulation, every equation points toward the same gentle truth: that the universe is larger, deeper, and more intricately connected than any one vantage point can reveal. What lies beyond the edge of the universe is not an ending, but a continuation. Not a boundary, but a widening. Not a void, but a further unfolding of the same cosmic order that shaped everything visible. The horizon is not a wall. It is an invitation to imagine the unseen with the same calm curiosity that once turned early starlight into understanding. Even the most distant galaxies, the earliest fluctuations, the faint relics of emergence whisper the same message: that the universe flows outward in ways no mind can fully trace, yet in ways governed by laws that hold everywhere. Beyond the edge lies more of this quiet structure, more of this ancient evolution, more of the pattern that shaped every atom, every star, every path through cosmic time. The beyond is not a separate place. It is everything that continues just outside the circle of light, everything that expands in silence, everything that remains real even when forever unseen. If this quiet journey brought you a moment of calm, a gentle like or a soft tap on subscribe truly helps keep this calm corner of the universe glowing. And tell me, where in the world are you listening from tonight? Rest well until our next quiet journey.